Thank you. So if you get too much of me, just remind me to be quick and short. Okay, and today I'm going to talk about the quantal response equilibrium and make it to be a dynamic evolution system and discuss the stability. So we'll first mention a little bit on why we're doing that, and not why that we are doing all our work on the stability. Why also for why QRE? Why we want to, some other people want to discuss quantal response equilibrium. And then we will come to the point that what is our own contribution and discuss stability of QRE, show a couple of examples, and show the final result. And then the rest will be discussion and question time. Okay, so what? We know that, sometimes I might actually wondering here and there, so if you lost my voice, just somehow remind me to come back to this microphone. Okay, so while we are actually considering models like quantal response, which assuming players do not take the best, but take the better with higher probability. Why we're doing that? This is a mathematical model of many other things that was hidden underneath the fact that the people are not choosing the best according to just the payment, the utilities. So the pure cash or pure happiness you can measure right into a utility. If you're using that, sometimes you will find out players not playing according to the strategy, which is the best option according to that utility function. So why? Then of course people suggest many reasons. Probably, for example, to keep a reputation you are a harsh man, then people will be nice to you. Or keep a reputation that you are a nice man, then other people will be nice to you. But anyway, reputation, or threats, punishment, reward, or discount, or insensitivity. Insensitivity means that it's just $10 on the table, I don't really care. If it's a million, then I probably will think differently. So anyway, there are many reasons that we're not choosing the best option. But the QRE people, they say, hey, I don't have enough information to tell which one it is. In that case, I just assume they will not take the best, but take the better to be with a higher probability. And of course, as a very ambitious picture of game theory, we really want to know more. Right? We want to know what are the roles of all these considerations played in that game theory and in the whole picture. Like, how can we write, for example, extended utility to include those terms which cannot, at the current stage, written in utility? Or even like we may consider, should we keep the idea of utility? Maybe we could just throw it away, starting from something else. Those are all possible. So those QRE work from other people and also from mine, just one step towards that goal that let's consider other things that make people not fully rational. It's called bounded rationality. But we want to know how. How can we describe such bounded rationality? And QRE happens to be one of them, but it's a very rough one. Okay, so that's the general idea of QRE. And very interestingly, this happened to physics too. We know in physics, a particle likely to stay on the bottom of the potential, which is the least energy state. Like if you have a ball, then a ping pong ball, for example, or bowling in a larger ball, then of course you see the stable place is somewhere around the bottom. But that's not definitely true. Something called Boltzmann distribution tells you, if you actually make the ball to be like in a finite temperature case, which means certain air particle, for example, hitting the ping pong ball all the time, then it will not exactly stay at the bottom. It will stay with the least energy state with higher probability, and the probability will be written as the famous Boltzmann form. And do not ask me why QRE people, they start to write their QRE in Boltzmann form, I don't know, but it happened to be the same. They actually just write down the same distribution function. And of course, instead of the negative beta, they got a positive beta. Negative beta means the least energy the better, right? Here is the positive payoff, the better. Okay, so after this introduction, I will just present you a horrible formulas. And for George's sake, I promise him there will be mathematics. So you're happy, right? So okay, so the definition of this is if we're going to use the game payoff matrix like that, then we define a evolution process that starting from PT, we how can get PT plus 1. So on the can we see it? No. One is dead. Is there any other pointers? Phase 1. Okay. So let's look at the right hand side of the equation. It starts from P at T. Thank you. And the left hand side is P at T plus 1. So this defines a evolution process. It's discrete time evolution process. And the original QRE was defined as the fixed point of this iteration. So the original QRE means if we start from some P1 star and P2 star, we end up with P1 star exactly the same, P2 star exactly the same. So it's the fixed point of this. And we just one more step further, very tiny step further to say, hey, we are now going to make it to be a dynamic process, not only a fixed point definition. So the original static QRE corresponds to this, and our dynamic QRE corresponds to this. But now the question is, these two, many times, probably not the same, right? Because this one required more than simply a fixed point. This one required to be a stable fixed point. Because we start from certain random initial condition, we do iteration, it end up at this row of infinity, beta. Then this has to be stable. So the first question we ask is, what is the difference between these two? And of course, there are other questions too that in the original QRE, we have to ask, what is the relation between this one to the NE? At the limit of larger beta, will this reproduce the NEs? And of course, this question has been answered partially. So roughly speaking, yes, the limiting solution of QRE are NEs. But there are actually occasionally some exceptions. So the theorem was not one-to-one correspondence. Some other people also still working on this. So the third question when you ask is, how we compare this to experiments. Can we now fit this to experiments? And of course, similarly, we need to ask the question, can we now compare this to experiments? So, in a sense, we are asking the question, what is the difference between our stable QRE to NE? What is the difference between our stable QRE to experimental results? And what is the difference between these two? But I will today just focus on the last and talk a little bit on the second. And basically, that's it. So the rest, I will just show you a bunch of examples, a few figures, and we are done.
Can I ask you a question?
Interrupt me anytime.
Aren't there any restrictions on the payoffs for your formulation to be applicable? If I remember correctly, you have to have a potential gain.
No.
No?
Not at all.
Okay, thank you. I'm sorry.
This is very important that the if you have a potential gain, then you can find out one bottom of the potential that actually the top, this in economics, that both parties satisfy. Therefore, it's a natural point that everybody stay. But without that potential condition, everybody's bottom is not the same bottom. So, but anyway, the formula doesn't matter. It still applies. Just the solution, there's no such clear picture as in physics. In physics, so clear that everybody trying to stay in the bottom, and there are other forces make it or not, but anyway, that's the picture. But in economics, that picture is gone. But mathematical formula, the definition, doesn't matter. So do ask me questions anytime. So good, thank you. Okay, and this slide is just one more scary mathematics, but if you don't understand it, just forget about it. I really intentionally do this for the physicists who are sitting there, if they are, that if you actually write in another form, instead of just A, B, and C, and D, which is, for me, it's more complicated. For me, this one is simpler. But this requires you to understand what is a Hamiltonian and what is the Boltzmann distribution. So I'm saying that if you're a physicist, believe me, this is indeed the Boltzmann distribution Hamiltonian. And then this makes the formula even simpler for me and simpler for other physicists. Anyway, there's just one slide more formula and no problem. There we go. Oh, those are a little bit of history, or we can skip that too. Okay, so looking at examples. So this example is a coordination game. We know we want to coordinate it to be at this state or this state, and even that will be better. But if you only look at the NE, there are 3 NEs. So the question is like, can we somehow point out, the difference between all the 3 solutions? And of course, if we actually using the dynamic process, you will find out that this is the line that the P1 equal to, P1 of t plus 1 equal to P1 of t. And this step kind of function, in the limit of larger beta, it's just a step function. It's the similar to best response function, but it's like twice of the best response function. Because you want to calculate the relation between P1 and P1, not P1 and P2. So it's like applying best response function 2 times. Okay, then you see the cross point of this curve to this straight line are the fixed point. And we usually find out 3 fixed points here. Okay, so that's it. Now we find out the fixed point. The central line here is very thin, so it's not very clear. Anyway, there are 3 lines here, but when beta is small, there's only 1 line. So sometimes we find 1 solution, and most times we find 3 solutions. And that's all this information there from original QRE. But we are saying, if we apply the idea of this dynamically stable or unstable QRE, we can tell a difference between the 3. We find out for this example, this one, the one corresponding to 1, 1 is actually stable, and the one corresponding to 0, 0 is actually stable for this region of beta. And the one corresponding to 0, 0 is always stable for all values of beta. But the mixed strategy is never stable. It's not stable at all. So if you actually using this to interpret how people actually play the game, which is not the thing that we really want to do, but anyway, let me assume we want to do that. Then we can arrive at the conclusion that in this case, this will be a better option, or this will be the case that most people will arrive at, because this one is more stable on the whole range of beta, and the mixed state is not a physical state at all, because it's never stable. And let's look at this. This corresponds to 0, 0. So 0, 0 is actually the 5, 5. So in a certain sense, this tells us how to pick up one out of a bunch of solutions, if we consider stability. If you don't consider stability, we cannot tell which one is the one. So using this example, I just want to emphasize this point, that stability tells the difference, distinguish all those QREs. Okay, so now let's look at another example. Oh, the colors are off. Anyway, this is a line that this is the QRE, and the lines the circles above the line are those stable QREs. And this game is very unique. This game does not have any pure equilibrium. It only has mixed strategy equilibrium. It's called tennis game. Then you find out only within the range of this beta, this mixed strategy equilibrium is stable. When beta is large enough, it's not stable. Okay, again, using the assumption, if we actually believe this is how people play the game, then we will kind of think that if now the experimental result is within those stable region, we will say QRE is good. QRE explains the experimental observations. But if the experimental result is more close to this NE, but on this unstable end, then we'll say, hey, maybe NE is better. QRE, although the whole spectrum of beta allows you goes towards NE, but it's worse than NE, if that is the case. And of course, if experimental result is somewhere here, like far off from both, then that means, hey, we're doomed. The current game theory, the whole thing probably is not, sufficient to explain the behavior. Okay, so that's the idea we're going to apply next. We will put one more pointer here, the pointer from the experiments, to see which one is closer to the stable region, unstable region, and NE, or the whole curve. All of the whole curve. Okay, so here are the games from, I think, who's the author? Anyway, I forgot. It's some famous example that many theories use to test the theory. I think Ross, but I'm not exactly sure. I pick up which three of those diagrams. Okay, so now let's look at those experimental results. This one is the experimental result. You see that it is exactly on the stable part, not on the unstable part. So this one means QRE is good. Oh, by the way, there's criticism on QRE, because you have one more free variable, right? With that, you can always do better than NE. So people criticize this is not really the theory that it should be, because you extended the idea, so you can always do better. And people actually do fit the experimental data by this QRE, doesn't pay any attention on what's the real value of that beta. Will that beta actually beyond the stable point? But we forgot to mention that all mixed strategy equilibrium, when beta is larger than certain beta C, is always unstable, because the best response curve. If you happen to be slightly over the left, next one you will even further to the left. Slightly over the right, next one you will even further left. So it's never stable. So you will have to check the beta is beyond this point, which is beta C or not, when you're using QRE. And here, for the first several experiments, in total, I think I run like, I collect data like 20, but I present in the paper 10. And this one stands for the 5 cases. So for the 5 cases, it is on the stable region. And here is somewhere in between. It's not that close to the NE, but it is still on the unstable region. If you really believe that people play game this way, then this should not be a case that support QRE. It should be, because it's in unstable region already. And there are cases it's neither close to NE, the stable region, or the unstable region. So this one, we have 3 results here, 2 results there. And we can, in principle, check all the experimental data and plot this curve, but we haven't done that yet. So okay, so that's basically it for this talk, and the rest, there's one more slide I want to show. Okay, so before that, any questions? So the major content of this talk, just that. Any questions? No? Good. Okay, so now I'm asking the question, how can we calculate analytically or almost analytically using certain assumption the beta c? So what we do is pretty similar to what you just did, but with a different equation of motion. Find out the simplified equation of the a single variable p, and that single variable p, the equation of the evolution of that p can be linearized on the fixed point, and then we find out the eigenvalues of the linearized matrix. Then we find out the beta c, and here is the comparison of our theoretical beta c and those simulation beta c. So for the games that we choose, we always run both a simulation and also analytical calculation of beta c, and they agree with each other quite good. Okay, so did I just speak the conclusion part? Okay, anyway, that's the conclusion part. Okay, so first we just extended the static QRE to a dynamic QRE, and then we find out the stability analysis can tell us can distinguish all those QREs, and more importantly, tell us that certain QRE are different from others. Because when beta is large enough, those QRE are never stable. So if your experimental results find out that it's in the region of those unstable QRE, you should be careful. It's not a confirmation of QRE is good at explaining experimental data. It's not. It's on the unstable region. Okay, time for questions.
Indeed, yes. Can I ask whether anybody wants to ask a question? I look around further. Anybody else? Okay, please go ahead.
Thank you for your talk, but can I ask a Chinese question? This is too many words that I don't know is English.
Okay, sure, no problem.
您好，就是啥啊？我想说个问题，就是您说您是个quantum 的量子的，其实波尔斯曼分布不是说量子的，波尔斯曼根本没有考虑量子这个东西啊。
No, it's quantal.
Could you translate the question?
So his question is this equilibrium quantal response equilibrium is quantum response equilibrium? He says there's nothing quantum. So it's just a misunderstanding. It's not a quantum, it's quantal. So I don't know why, by the way, who can tell me why economics call it quantum?
Okay, I know this word quantum, another question, that is, for your Hamilton function, can I say this page?
You want to find the formula for physicists?
Yeah, I want to say the Hamilton function.
Formula for physicists. Finally, I found the physicist.
Okay. That is this function. I just say it in Chinese.
No problem.
是怎么定义的？这个用那个物理学中这个就是能量函数出来，就是这个能量函数是能加动能。您是怎么着找到这个用这个支数？因为我一直在想个问题，用这个支数矩阵怎么去表征这个能量的问题？因为生物学中很多有这个问题。
Okay, so I'm going to translate the question first and then give the answer. So he's saying that since I'm using Hamiltonian, how in this game I define my Hamiltonian? Which is very good. I actually really like to talk about it, but I worry there's no physicist sitting here, so I skip this part. Good, thank you very much. So the idea is, hey, we're starting from here, the payoff matrix, right?
Yeah.
And we want to write H12 according to the G12, right? So the H12 will be very easily that just stretch the matrix to be diagonal. For example, I can give you one expression. H1 will be A here, B here, C here, D here. H2 will be A here, A prime here, C prime here, B prime here, and E prime there. So for this example, that answers your question, right? And of course, you might ask me how I can do that, but that we have to discuss later.
Any other questions? Yes, William.
Thanks for your very interesting talk. Although I missed the first part, but you know I know your work. Okay.
Yeah.
So my main question is that you said maybe all the equilibrium are unstable. In that case, what's the dynamics look like? Would you give the
yeah,
else or?
Yeah, sure. I will. Thank you very much. So let's first look at the real dynamics first, and then show the diagram. So this happened to the fixed point here, for example. This fixed point later on will become unstable. Why? Because if you iterate it, every time it goes to the 1, 0, 0, and 1, 1, 0, 0, and 1. Okay, so now this is a real dynamic process. And if we're going to look at this phase diagram, those green dots are the trace of that. So if we really plotted it on the phase diagram anyway, then we see it run away. It will not stay at this spot. So I just show one of this point in the iteration, how it leaves from that stable point, sorry, from that fixed point.
So based on your answer, may I ask the second question?
Yeah.
So now you have the dynamics. So if you compare this with the experimental results, could you find that the player updates their strategies like your prediction?
We haven't done that. We have thought about a really long time. But you know, studying the learning process is a whole area different from studying the equilibrium problem. So we have talked to some people, get the data of their iteration, repeated again. But from our initial comparison, it's not that good. But we haven't worked out detail yet. So Professor D's thinking that he should have got another PhD student work on that. But yeah, so this work is done me together with Professor D and one of his PhD students. So with all that PhD student, who knows when the idea will be implemented.
May I add a few comments? Because at the first time you told me this, I was shocked. Because at the very beginning, we use quantal response methods to explain experimental behavior. And we only consider the average strategy of the players. So we never consider the stability. So this, for me, is very sad. You know, I use quantal response method to do equilibrium selection, and it's a unique behavior. And finally, you're talking that it's unstable. So this cannot work in the experiment. So it's very sad.
But not all of them are unstable. Oh, yeah. Those with pure step strategy equilibrium, those are stable.
Right. I just wanted to add maybe two rather naive questions. From my background, I know that very similar methods are used in a field called random choice theory. This is often used for marketing research or public operations research.
Yes.
So people define a utility and then a probability of action, and they are related to e to the power of minus utility.
That's right. That's
probability of action. And then, or the relative probability or the relative weight of an action, I should say, that you have to normalize with the probability. So that sounds quite similar. It's
very
right?
Yes.
So would you like to comment on the relationship with random choice theory?
So the only difference here is on the game setup. There is a decision-making setup. So that's the only difference. And it has a very interesting story behind it that, as far as I know, which I'm not guarantee is actually accurate, that physicists start to work on this game theory setup, the randomized strategy, and also decision-making theory that almost at the same time on both branch. But economicists, they actually work on decision-making theories, they work on decision-making first. So they have totally different development traits. They are not actually, until very late, they actually merge to each other. So for me, when I do this work because the idea was proposed in 2004 in a work of quantum game. I don't know anything at all on quantum response equilibrium. I say I just wanted a Boltzmann distribution. If you ask me why, I just tell you, we're physicists. We want a Boltzmann distribution, that's all. But economicists, they're constantly asking why, in what condition, they call this logit response form. Logit response form can appear. They ask constantly the question. There are many research papers trying to answer how this function actually emerged. But as a physicist, I don't really care. Just like I use Boltzmann distribution all the time.
I appreciate that honesty. Very good. Now two other small remarks. You were wondering why is it called quantal? In my understanding, it's the same meaning as what IIASA referred to of Eleanor Ostram's research as gradual or graduated, actually. It's really the quantitative or quantal response to the utility difference. That's how I read it. And that has nothing to do with quantum, which actually stresses the discrete. It stresses
a small
continuum
quantity. Right. That's the idea of quantum. Yeah. So quantum is still a small quantity, but it's like in a gradual manner moves that direction.
Right. And I would read it as gradual, like that. Probably it's easier to communicate.
Yeah.
Now, the other point is, in many studies of corporation evolution, people have studied errors, perception errors, and in particular implementation errors. So that seems very similar in spirit to the quantal response.
Yeah.
Except that what you see here is that when the utility difference gets really large, then the implementation error probability goes down, and when it's very tiny, then it's really high.
Yeah.
So one would have to argue that it is this feature, this proportionality somehow of the error making to the utility difference that must drive some of your results, because often it is found that corporation research results are quite robust, at least up to a point, to these errors.
Yes, so I think you are entitled to that kind of belief or interpretation. That's fine. But in physics, we have our understanding why that happened. We know that it's because heat, because temperature. When there are temperature, there are noises. When there are noises, it will not stay at the least energy state. So in physics, we do understand what is the reason. Although not really, because if you ask me what is temperature, then again, I don't have answer. So that, to a certain degree, I have answer. But back here in this example, then you ask me if it is because I don't really care so much, $10, or if it's because I'm stupid, I'm not intelligent enough to tell the difference. I don't really know. So in the case of game theory, we do not have the background of picture to interpret it. In the case of physics, we kind of do.
Yeah. Sorry, since I'm a theoretical physicist, I also feel like indulging on this a little bit more. Hopefully it's not boring everybody. But just one point, you know Shannon's theory of entropy is translating the traditional physics view of entropy into an information theoretical context. And in that context you can interpret the expressions, the Boltzmann-like expressions.
I know where you are going.
Just in terms of maximum entropy arguments.
Yeah.
So you don't need to invoke physics, you just need to invoke maximum entropy argument in the informational theoretical sense.
Yes, I agree with you that if you actually use information point of view, this can be interpreted. Yes, but that's like another principle, studying another principle instead of that is something we don't know.
Right, but that answers the question, why do we use this form? It's not arbitrary, it's not just convenient, it can be derived as strict assumptions. Okay, any other questions? Right, then the second part of the double pack is about to start. Thank you for your willingness to give 2 talks.